Hi, welcome to section 7.3 on estimating a population mean. In the last section, we learned about estimating a population proportion based on using a sample proportion. And in this section, we're going to learn a somewhat analogous process for using the sample mean to make inferences about the value of a corresponding population mean. So some key concepts here. We should know that the sample mean, or X bar, is the best point estimate of the population mean. So this is similar to what we saw in 7.2 with the population proportion. We're going to learn how to use sample data to construct a confidence interval where we can estimate the value of a population mean. And we're going to learn how to interpret those values. And we're also going to develop the ability to determine the sample size that's necessary to actually successfully estimate that population mean. So some requirements. The procedure that you're going to learn in this chapter has a requirement that the population is normally distributed or that the sample size is greater than 30. A couple of things about margin of error. You're going to notice in this slide that the slide is a little bit messed up. It's missing some information, and that's due to I'm doing this presentation on a Mac. But so I would encourage you to look in your in the actual text. Use the multimedia textbook through MyLab to be able to fill in the blanks on this. But essentially, you're able to calculate a margin of error. Just like we saw when we did our margin of error for population proportion, you can also calculate a margin of error for an estimate of the mean. And you can do that and this is with when your standard deviation is not known. And so again, you're gonna have to look at the actual slide to get the formula that goes in here because it's not appearing in this version. But essentially, this formula has n-1 degrees of freedom, which we'll get to in a few minutes what that means as well. All right. They talk a little bit here about student t distributions. So if the distribution of a population is essentially normal, then basically what you can do is you can say that any distribution of a smaller amount is also considered normal. And so you're able to calculate what they call a student t distribution, which is basically saying that for all samples of the same size n, that if your population is normally distributed, then they should be as well. And this concept is often referred to as a t distribution, and it's used to find different critical values. And so again, this is another slide where it's not the formatting of the way that the formulas were put in is not compatible with PowerPoint, and so you will have to go into the text, and there is a section on student t distribution to fill in these formulas for yourself. Okay, so some definitions. So the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all the values. And basically, that's done through degrees of freedom. And we abbreviate degrees of freedom by DF. And basically, degrees of freedom are basically n, which is your sample size, minus 1. And we're going to learn some different methods in this section where we're going to use these degrees of freedom. Okay, so some notation before we move into our next section here and we get into some of the formulas. So here's our symbol for a population mean. Here's our symbol for a sample mean. So keep that in mind. In this course, we've mostly been focusing on sample statistics, but in this section, as we saw in the last section, you'll also have a little bit for the population as well. Then we have lowercase s for our sample standard deviation, n for our number of sample values, e is our margin of error, and t with this symbol is actually our critical t value. So just like we saw in the last section where we had a critical value with a z-score, here instead of a z, we have a critical t value. But it actually does a very similar function. It separates an area of basically, half into kind of a part of the right tail of a distribution. And so it's very similar and analogous to what we saw in the last section with sample proportions, except here we're applying it to sample means. Okay, So when you're going to calculate a confidence interval, and again, this is not really cooperating with me in terms of the formulas, let me show you this because this actually shows it better because this has the formula that we're going to actually use. So here's actually our procedure for constructing a confidence interval when you have a standard deviation that's not known. So you're going to verify that all the requirements are satisfied, and then we're going to use n-1 degrees of freedom. And there's a table in your book that can be used to find those critical values that correspond. So just like before we were using a z-score table to be able to do this, in this section you're going to use the table A3, which you can find in the multimedia text. We're then going to calculate a margin of error, and then we're going to create and construct our confidence interval, which is going to be our mean minus our margin of error, and our mean plus our margin of error. And when you put those together, it creates the confidence interval. So this side will be the low end of the interval, and this will be the high end of the interval. And we're able to estimate that our population mean falls within that range. And then we're able to round and make those confidence interval limits, similar to what we saw in the last section. Okay, so here's an example. A common claim is that garlic lowers cholesterol levels. In a test of effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after. The changes in their levels of LDL, which is a type of cholesterol, in milligrams per, let's see, something liters, I'm not sure, deciliters, I think, have a mean of 0.4 and a standard deviation of 21. So we're given our mean and we're given our standard deviation. And we're going to use sample statistics of n equals 49. We have our mean, so this is for our population, and this is what we actually have to play with for our our sample statistics. So our n is 49, our x bar, which is our mean, is 0.4, and our standard deviation is 21. And we're going to construct a 95% confidence interval that's going to estimate the mean after this treatment with garlic. And we're going to then answer the question, what does the confidence interval suggest about the effectiveness of garlic in reducing these cholesterol levels? Okay, so are the requirements satisfied? Yes, you have to have a simple random sample, and you have to have an n greater than 30. Those were the two requirements that we were shown at the beginning of this PowerPoint. So it does meet those. All right, 95%, similar to what we saw in the last section, implies basically that, think of how to explain this, that this is really that, if you come back, let's see, here we go. It's part of that critical value, and that it's that value that we're going to divide by 2, which really separates it into either end of the distribution that we're seeing here. So let me, bear with me. Okay, coming back. All right, so we have that. We know our n is 49, and our df, which is our degrees of freedom, is going to be n minus 1, which is 48. So the closest df, the degrees of freedom, is actually 50 with 2 tails. And so you're able to actually calculate out what that degrees of freedom would be. And so we're able to use those numbers to then estimate and actually calculate that margin of error. So that's what this is here, that margin of error. So let's plug everything in. So we basically have our critical value. Then you have, which again, that critical value, once we went through and did our degrees of freedom, we found to be 2.009. Then we're going to multiply that by our standard deviation divided by the square root of n, which is 49. And then basically when we do out that math, we wind up finding our margin of error is 6.027. Then we can plug that into our confidence interval. So we know our mean, so we're going to, on one side, take the mean and add our margin of error, and on the other side, we're going to subtract our margin of error. And so we wind up with this range where basically your population mean based on a sample mean of 0.4 is estimated to be somewhere between -5.6 and 6.4. So we are 95% confident that the limits of negative 5.6 and 6.4 actually do contain the value of the population mean. Um, and the mean, and this is the mean of the changes in the cholesterol levels for this population. So because this confidence level limit contains the value of 0, it is very possible that the mean of the changes in this cholesterol could also be 0. And what that means when you're looking at the basically this bottom question is if it's possible that your mean is 0, it means that that treatment is not very effective. And that's what was the takeaway from this example. Okay, so some other important properties to pay attention to for student t distributions. So the student t distribution is different for different sample sizes. And we're going to see that there's, we can kind of look at this in a moment. We'll flip to the next slide. The student t distribution has the same general symmetrical bell shape as a standard normal curve, so similar to what we saw before, but it reflects the greater variability, basically, with wider distributions than is really expected with small samples. With a t distribution, you have a mean of 0, just as the standard normal distribution has a z equaling 0. The standard deviation varies with the sample size and is greater than 1. So in this case, your standard deviation won't be 1, it'll be greater than 1. And as the sample size gets larger, the student t distribution reflects closer and closer to that normal distribution, similar to what we saw in the last section with z-scores. So here is actually a distribution that they've done, so you can see. So our standard normal distribution is this blue line. So you can see it goes up, crosses over, and comes down the other side. Now, in contrast with that, here's our student t distribution for an n of 3. So for 3. And you can see it follows a slightly different path than that standard normal distribution does. And in contrast with that, if you go up to an n of 12, you can see that that even has a slightly different path. That gets closer. See how the n of 3 was further away from that standard normal distribution? But as you get your n increases, like to 12, you can see it starts to even more closely parallel that standard normal distribution. So the bottom line is the greater your n is, the closer it's going to mirror that standard normal distribution, and the smaller your n is, the more variability that you're going to see on the graph. Okay, a couple of other things. We can find point estimates and E from a confidence interval. So once you have a confidence interval, you can actually make these estimates. So if you know your upper confidence limit and your lower confidence limit and you divide by 2, it gives you a point estimate of your population mean. And so if you're ever given a problem where you're given your confidence levels or you've been able to calculate them, you can then come back and do this point estimate for the sample or for the population mean. Similarly, you can also calculate a margin of error, which is your upper confidence limit minus your lower confidence limit divided by 2. And that will actually give you an estimate of your margin of error as well. So you're able to calculate both of these if you have a confidence interval that you're given. And okay, another topic in here is how big does our sample size really need to be in order to effectively estimate that population mean? And so there's a few things that we need to look at here. Now, granted, again, this slide is a little messed up because of the formatting, but let's see if the next slide gives it better here. Let's see. I'm trying to see if I can find a good example of this. All right, let's walk through this, but understand I'm going to define these symbols in a moment because they're actually, you can actually see all the symbols here. It's harder to tell on that other slide. So you have your critical values, you have your Z that corresponds to that critical value, you have your margin of error, and you have a standard deviation. And essentially that's really what they're spelling out here with those symbols. So just pay attention to that example and you'll be able to kind of fill in the blanks that go on this slide. So again, I apologize about the formatting. Some things about rounding off rules. When you're rounding off sample size, you're always going to round to the next largest whole number. And the reason why, imagine that your sample size is people. and you have, 8.5 people. Well, if you round down to 8, that's not enough people. But you can't do 8.5 people. There's no such thing. So you have to round up to 9. So this is very similar to what we saw in 7.2. You'll always round to the next largest number. All right. This gives you kind of the process for going through this, but I think it's actually easier to jump into the example. And you're welcome to kind of walk through the theory of this. But basically, we're going to use the data that's given to us in the problem to then estimate this sample size that's needed. So here's an example of a problem like this. Assume that we want to estimate the mean IQ score for the population of statistics students. How many students must be randomly selected for IQ tests if we want a 95% confidence that the sample mean is within 3 IQ points of the population mean? Okay, so let's look at everything we have here. First things first, we're given a confidence level of 95, which corresponds with a critical value with basically a delta of 0.5 and a critical value of 0.25. When you look this up on a z-score table, you find out that that corresponds to a z of 1.96, and we saw that before in the last section, that anytime you're doing 95%, your z will always be 1.96. E is our margin of error, and they're telling us what they want our margin of error to be. Basically, it's 3 IQ points. 3 IQ points plus or minus is the margin of error. And then finally, we're given how many students, I'm sorry, where are they getting the standard deviation from? Not sure where they got that standard deviation from here. I love it when they don't explain things very well in here. Oh, boy. They don't really seem to do out the rest of the example. What is that? Oh, no. I'm sorry, guys. All right. Well, let's just kind of, I guess, look at what they've summed up here, and I guess we'll have to go from there. I'm really sorry that my slides are not cooperating with me very well tonight. But anyway, what they were able to do is actually use all of this data to find out that you only need to sample 97 students to be 95% confident in this, but they don't actually show you any of the calculations. So I would recommend looking in the book. This example should be in the text, in that multimedia textbook, and it'll walk you through exactly how they did this calculation. I really thought that on the next slide they presented it, but they don't, so I apologize about that. So please definitely consult your textbook as you're going through this section. Unfortunately, again, the formatting is just not playing nice with my computer as I'm going through and making this lecture video for you all. Okay. Couple of other things. There's a second part to this, which is really that these are methods where we can actually, again, estimate population means. But here, in this case, it's times where we also have to know the population standard deviation to be able to do this. So this is where we have a known standard deviation, whereas before, if you'll remember, we had a standard deviation that was not known. And so here we're actually going to be given the standard deviation. So the majority of the symbols are all the same as what we saw in the previous section, except here standard deviation is also included. And so here, some things about this. The sample has to be a simple random sample, again. The value of the population standard deviation, it has to be known. And the population either has to be normally distributed or the n has to be greater than 30 or both of those things in order to be able to use this formula. And so here is your formula. So we have the mean minus our error is less than our population mean, which is less than our sample mean, added to our margin of error. And E in this case is going to be equal to our z-score with the critical value. So like for a 95%, this would be 1.96 times our standard deviation divided by the square root of n. And this can also be broken down as x plus or minus e, or x bar minus e, comma, x bar plus e. So it's the same process as what we saw before, nothing different. It's just sometimes they like to play around with the notation a little bit. Okay, so here's an example for this. People have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably. So we need to update our estimate of that mean so that boats, aircrafts, elevators, and other such devices don't become dangerously overloaded. This is a real problem. If you ever go into an elevator, you'll see that there will be like a certificate, and it will actually say a max load. Now, when they built elevators originally, they estimated that a certain number of people were going to be able to ride the elevator at one time. But over time, as weight has gone up, especially with like the obesity epidemic and other factors, those mean weights were never really re-updated. And so that's really what this example is getting at, is that, this is a real life example of a problem that people in this industry would face. And so we're going to use the weights of men from a random sample. And so what we get from our random sample, we had an N of 40, we get a mean weight of 172.55. And research from several other sources suggests that population of weights of men has a standard deviation of about 26 pounds. So this is our sample data, and then this is the overall data that the larger population data. So we do have a known standard deviation. So we're going to use this information. Basically, we're going to find the best point estimate of the mean weight of population for men. We're then going to construct a 95% confidence interval. And then we're going to look at the results and ask ourselves, what does that mean? What does that suggest about a mean weight of 166.3 pounds that was previously used to determine safety? Okay, so here is our calculations. So the sample mean is the best point estimate of the mean weight of the population, and we're given the sample mean in the problem, 172.55. So we're going to use that as our point estimate of the mean weight for the population. A 95% confidence interval implies, as we discussed, this is going to be our z-score, 1.96, and then we're going to calculate our margin of error. So we're going to take the standard deviation that was given to us of 26 pounds, so 1.96, which is our z, times 26, which was our standard deviation, divided by the square root of the number of men that we surveyed, which was 40. And we find that our margin of error is 8.057 and change. Then we're able to, the same way we've done before, construct a confidence interval. We're going to take our point estimate for the mean weight of the population, and we're going to subtract our margin of error, and then we're going to add our margin of error. And from there, we find a range of 164.49 pounds to 180.61 pounds would be, you'd be 95% confident that your mean weight for your population of all men would fall between there. Now, based on the confidence interval, it is possible that the mean weight of 166.3 pounds used in 1960 could still be true today, because that falls within the range that we were able to calculate. However, the best point estimate of 172.55 pounds suggests that the mean weight has gone up. And so, you can imagine, though, that this is actually, could potentially be contributing to safety-related issues on vehicles like this, boats and aircraft and things like that. And so it's really important that when you see data like this, and in this case, this would indicate that they should do a lot more research and probably update these assumptions, some of these assumptions about mean weights, and do a larger study. So that's what they're concluding here. All right, so the bottom line is that when you're doing these, this little chart kind of walks you through whether you're going to use a z-score or a t-score. So if you know your standard deviation, you're going to use a z-score. And if you don't know your standard deviation, you're going to go the t-score route. And then you have to, kind of follow the steps through here to determine what you need to do. And so, there's some other kind of breakdowns here, which is basically, this is basically saying the same thing. It's just doing it in a different form. But again, don't overthink this section. It's very similar to 7.2. You're using sample estimates or sample data to make conclusions about your larger population. And you're using confidence intervals to help you understand how likely it is that you've gotten a correct estimate, or basically telling you how accurate that sample estimate really was compared to the population. All right, so that ends section 7.3. Next up, chapter 8.